So, example number 5, evaluate the integral from -3 to 3 and from 0 to the square root of 9 minus x squared for the function sine of x squared plus y squared dy dx. That's all they're giving us. They're giving us the integral. Number 1, we have to figure out the domain of integration. We have also from there, we will sketch the region of integration. Okay, so that means, number 1, let's state the domain. The domain of integration of the set of all order pairs x, y such that, so x is varying between -3 and 3, and y is varying between 0 and the square root of 9 minus x squared. All right? So let's use this information to sketch the region of integration. Any ideas of what this set looks like? Yes. It's a semicircle, right? So, well, since these are functions of vex, yes, it could be an upper semicircle or a lower semicircle. What's this one? The upper or the lower? Huh? The upper. How do we know it's the upper? Well, yes, -3 to 3. Well, that's the how. But I mean, how do we know it's the well? The -3 to 3 is just horizontal distance. But how do we know the semicircle? It's the upper one.
Y is greater than 0.
Y is greater than 0, or we have the positive radical, right? So let's sketch the region. Okay, so the reason why we first sketch the region of integration in the world of xy, that is to figure out what are the limits going to be for the world of polar. So that means, okay, from y equals to 0 up to square root of 9 minus x squared, and yes, this still goes between -3 and 3. So let's shade our region of integration. Okay, that means, okay, I think this is good enough for us to, well, from -3 to 3, to write the domain of integration to the world of r theta. All right, so this is telling us that the radius varies between 0 and 3, and the angle in this case, what about the angle? Thank you. 0 and pi, right? So we got it. We got this figured out. All we need is to set up the integral. Oh, okay. So let's talk about the integral. Number 1, this x squared plus y squared, what is that equal to? R squared, and dy dx becomes r dr d theta. Now, think about this. So if you wanted to evaluate this double integral using the world of rectangular, not possible. Even if you change the limits of integration, that's because, okay, if you said the u equals to x squared plus y squared in integrating with respect to y, you would have a 2y. But you're missing the factor of y that stands the u part of the problem. Same if you reverse the order to dx dy. So, but lucky for us, we can change this to polar coordinates. But yes, still, this x squared plus y squared, which is equal to r squared, are still going to give us potentially the same problem with the square. But the good news here is that when we change from rectangular to polar, we get this extra factor of r that will send the du part of the problem, which is great. All right, so let's get started with it. So that is the double integral, the integral from 0 to pi and from 0 to 3 of sine of r squared times r dr d theta. Okay, so let's set up the u substitution. U equals to r squared du equals 2r dr. So r dr equals 1/2 du. Okay, so that means, oh yes, let's change the limits also. U of 0 and u of 3, that is 0 squared and 3 squared, which is 0 and 9. Alright, so that is the integral from 0 to pi, and then the integral from 0 to 9 of sine u, and then that times 1/2 du d theta. So the d theta, it's still just d theta because we're focusing on integrating with respect r. So the d theta remains there. Okay, so let me take out the 1/2 outside, or actually let me just integrate this. Why not? So this will be the integral of sine, careful, that's negative 1/2 outside from 0 to pi. And what's that? Cosine u from 0 to 9 d theta. So upper limit minus lower limit, so that is negative 1/2 integral from 0 to pi. That's cosine 9 minus cosine 0, okay, d theta. And well, in this case, cosine 9 is not going to be one of those exact values that we know from the unit circle, so just leave it as cosine 9. However, cosine 0 is. So this will be negative 1/2 times the integral from 0 to pi. I'm going to write it, well, no, that's fine. Cosine 9 minus 1 d theta. So I'm going to do two things in one shot here. So number one, I'm going to take that cosine of 9 minus 1 because it's just a multiple constant outside of the integral. And I will also use this negative to reverse the order of these two terms. Okay, so that'll be 1/2 1 minus cosine of 9 integral from 0 to pi on the theta. And the integral of d theta, it's simply theta. That is theta evaluated from 0 to pi. Pi minus 0, that's just going to be 0. That equals, okay, 1/2 1 minus cosine of 9 times pi minus 0, which is simply pi over 2, or 1 minus cosine of 9. All right? So that's going to be our answer here. Okay, so for this first couple of exercises, these are basically to have a look at the mechanics. How do we go from the world of rectangular to the world of polar? Notice in this case it was just evaluate, but not really the application. What do these integrals represent? Well, even though you already have some notions about what these integrals represent, because here, what are we integrating? We're integrating some f of x other than 1, so that must represent volumes. Same with the previous exercise, that also must represent volume, but it's not set up as such. It's just a generic problem, evaluate the integral, and that's it. Now we will put geometry to it. So find the volume of the solid bounded by the plane z equals to 0. Another way to say z equals to 0 is the xy plane. Just so you don't freak out when you see these problems worded differently, you may either see xy plane or simply z equals to 0. And the paraboloid given by 1 minus x squared minus y squared. All right, so let's have a look at GeoGebra and see how this looks like. Okay, so let me open. So from my files here, okay, polar. So this is how it looks like. So what do we have? We have this paraboloid opening down because of the negative square terms, and it's bounded below. Okay, so it's bounded below by the xy plane. Okay, so let me get rid of this. Yes, perfect. Let me zoom in a little bit more. So having this picture here, we can always rotate this solid so we can see the XY projection, all right? That's to help us see what limits of integration will be for the angle. And in this case, as we can see, it's the entire circular region. I think it's easy to see that the limit for the angle is going to be 0 to 2 pi, all right? Do we all agree with this? Now, what's next here? What about the radius? Well, so I mean, it's easy to see that we're going from the origin all the way to radius 1 from the GeoGebra project here. Let me see if I can. Let me get rid of the surfaces so you can see the circle that actually it's the intersection between the paraboloid and the plane below. All right. So with just a circle in the picture, we can see it's a unit circle. So that means the radii varies between 0 and 1, right? So I think we have everything we need to set up the integral and calculate the volume of the solid contained bounded below by the xy plane, that is z equal to 0, and bounded above by the paraboloid, right? Let's go about that. All right, so now, algebraically, in many cases, you are still required to algebraically show some work. So remember this unit circle we got as the intersection? We still need to show this algebraically. How do we get that? Because again, we're looking at the intersection between two surfaces. So the intersection between two surfaces right here, that is this circle. Let's show this algebraically. Number one, intersection set these two equal to one another. Z equal to 0, z equal to 1 minus x squared minus y squared. Set the two equal to one another. That's to get 0 equals to 1 minus x squared minus y squared. Move all the x and y's to the right to the left hand side. Hey, isn't that the equation of the unit circle? So that's how we show algebraically that the two surfaces, the plane and the upside down paraboloid, intersect at a unit circle. All right? And all you may be asked to plot is the projection onto the xy plane. That is that circle we just saw on the GeoGebra project. All right? That means this circle. Perfect. All right. So, okay, the domain of integration here, number one. So, if we were to solve for y right here, that would have been y squared equals to 1 minus x squared. Y equals plus minus the square root of 1 minus x squared. So, the domain of integration right here would be r x y such that, okay, careful, x varies between -1 and 1. I think this is kind of clear, right? Now what about y? It's bounded above by the upper semicircle and bounded below by the lower semicircle, described both by, okay, so y is varying between negative root of 1 minus x squared and positive root of 1 minus x squared. Guys, do you feel like integrating this? Do you feel like integrating that? No, right? No, you don't want to integrate this because no, it's not a feasible task to do. Okay, so anyway. So let me get rid of this. So instead, that's why we have a powerful tool called polar coordinates. We're going to go from the world of xy to the world of r theta, right? And well, I think it's easy to see the limits, and they're going to be a lot simpler. That is, the radius varying between 0 and 1. Careful, I know it goes between -1 and 1, but there's no such thing as negative radii. It's all from 0 to 1 because we're going from the pole to any point on the circle or the circular region, and that's always 1 unit or 2 units or 5 units depending on the radius of the circle. So there's no negative radii, all right? Just keep that in mind. What else? Okay, so the angle in this case, we already agreed that the angle goes between 0 and 2 pi. That is the entire circular region. Let's set up the integral. Okay, so a volume integral V it's a double integral of the form double integral over the region R of the function f of x y dA. Okay, so let me write the integral in what's it called in rectangular without writing any limits. Okay, so number one, what is this f of x y? Recall, this is not top minus bottom, not rightmost minus leftmost, is roof minus floor. Okay, which one is the roof, which one is the floor in here, in this situation? Any ideas?
Is the square of the roof is the square of 1 minus x?
Yes, it's that's correct. And the floor?
Is the negative square root?
Not okay. Let's have a look at the GeoGebra project. Okay, so the roof, isn't that the paraboloid? This paraboloid? Hey, come on. Yep. Hold on. I don't know why it always freezes. Okay. I have to close and open again. All right, polar example 6. Okay, there you go. So what's the floor? Z equals 0. What's the roof? The paraboloid, right? Z equals 1 minus x squared minus y squared. Let me go back to the notes. So that is the double integral over the region R of top, which is 1 minus x squared minus y squared, minus 0. I know it's silly to write down that 0. dA. Let me just label it. So, roof, floor. All right? Well, no, I'm not going to iterate this integral in terms of x's and y's. We already saw the limits are going to look crazy. We're going to use polar. That is the double integral from 0 to 2 pi and from 0 to 1 of 1 minus r squared. How about that? And dA, which is r dr d theta. All right, let me distribute the r over the terms inside of the parentheses. That is the integral from 0 to 2 pi, from 0 to 1, r minus r cubed dr d theta. So we're integrating with respect r. Well, this is a very simple polynomial to integrate. That is the integral from 0 to 2 pi. That is 1/2 r squared minus 1/4 r to the 4th from 0 to 1. d theta. Okay, keep going. That is the integral from 0 to 2 pi. Well, that is going to be 1/2 1 squared minus 1/4 1 to the 4th. But when we apply the lower limit of 0, do you guys agree that everything is going to get zeroed out? Okay, just go for it. Minus 0 d theta. So that's going to leave us with the integral from 0 to 2 pi of 1/2 minus 1/4 d theta, which is going to give us 1/4. Let me write that 1/4 outside of the integral from 0 to 2 pi, and that's d theta. Do you see how simpler these integrals become? That otherwise, in the world of rectangular, would have been, well, from hard at least to impossible, because we wouldn't have the tools necessary tools to evaluate. Although there's other more advanced methods of integration, well, we don't have those methods, we don't have those tools, so instead, polar coordinates. So that's pi over 2 pi over 4, which is pi over 2. So that's the volume of this solid, right? Of solid bounded above by the paraboloid and bounded below by the what's it called? Yeah, the xy plane, z equals to 0. Let's have a look at another volume problem. Why not? So, let's see. Find the volume of the solid that is inside the hemisphere, z equals to 16 minus x squared minus y squared, and outside of the cylinder, x squared plus y squared. So, okay, let me open another, well, let me open a new GeoGebra problem here. Okay, so essentially we want to look at the intersection between what's that? The square root of what is that? 16 minus x squared minus y squared. Right? And what else? The cylinder. Oh, I needed the 3D version of it. Okay, let me open that again. Okay, GeoGebra 3D graphics. There you go. So z equals to square root of 16 minus x squared minus y squared. Okay, that's the upper hemisphere. And what else? The cylinder, x squared plus y squared. Oh, no. All right. Equals, is that equal to 1? Yes, equals 1. All right. So this is what we want to find the volume of. That is, think of this cylinder drilling the upper hemisphere, so like a washer, right? Like one of those solids of revolution with an empty space in between. Well, I have a better project for this, so you can see, because with this it's not easy to see what exactly are we finding. Okay, let me show you the other file instead. Okay, polar example 7, no, discard. So this is what we're looking for, what we're looking at. Let me rotate it so you can see it. So much better. Isn't it easier to see? We're finding the volume of the solid bounded below again by the xy plane, all right, and bounded above by the upper hemisphere, but with an empty space in between. This, so we can easily see this donut. Do you see this donut again? We have been looking at this donut, so we can easily see the limits of integration for the angle. So for the angle, I think it's obvious it's going to be from 0 to 2 pi, because it's spanning the entire system here. However, it is the radii that is going to change. Let's see. So we're going from radius, what is it? It's hard to read, but it's 1, 2, 3, 4, from 1 to 4. So that's going to make our job a lot easier rather than going in the xy direction. Okay, so let's see. So, all right. Now the thing is here, for this one, I'm going to skip the what's it called? I'm going to skip the domain in the xy direction, because it's simply not a well, actually it's easy. It's not that hard. It's not that hard, because for the domain R of integration, that is all the other pairs xy such that x squared plus y squared is between 1 and 16 in a compact way, right? So inside the circle of radius 4 and outside of the circle of radius 1. That's what this means essentially. All right, so now that we saw the picture here, let me do one real quick. So that is unit circle of radius 4. All right, and shade. So that's going to be the entire donut here. Let's shade accordingly. All right, and we can already write our domain of integration. That is R in the world of r theta, that is, what's that? Okay, so the radius here clearly varies between 1 and 4, while the angle goes between 0 and 2 pi. That is the entire rotation. So how do we know it's the entire rotation? Well, that's because there's no additional conditions, because another piece of information or condition that may change this is maybe find the portion of the volume in the first octant. All right. If it said, for instance, the first octant, then it would have been from 0 to pi over 2. All right, that's the only thing that would change, and we would only have a quarter of the result that we're going to obtain in this integral. All right, let's go for it. So volume, which is a double integral of a function f of x y when f of x y is other than 1. If it's 1, again, that's just going to take us to the area. So that is the integral. I'm not going to iterate anything. Again, roof minus floor. What's the roof? Isn't that the hemisphere? Square root of 16 minus x squared minus y squared minus the floor, which is 0 in this case. All right? dA over the region R. So this will be number 1. Now let's go about polar. 1 to 4 and 0 to 2 pi. What is this? 16, the square root of 16 minus x squared minus y squared, that is r squared, and dA becomes r dr d theta. Do you see how we wouldn't have been able to evaluate the double integral? Well, actually it would have been possible, because maybe we can set up a trigonometric substitution with 2 variables. That's possible. Yep. Sounds weird, but it's if you think about it, it's doable. So you can set your, in this case with respect y, so this number would be the constant, the 16 minus x would be the constant part, and the variable part, the y variable. But it's going to look a little weird. Let's just go about polar coordinates. And again, this is going to be a pretty cool u substitution. That is u equals to 16 minus r squared du negative 2r dr. r dr equals negative 1/2 du. Again, change the limits. U of 0 equals to 16 minus 0 squared, which is 16, and u of 4, that is 16 minus 4 squared, which is 0. I know this integral is going to look weird, but we have worked with these integrals before a good number of times. So 0 to 2 pi, integral from 16 to 0 of the square root of u times negative 1/2 du d theta. So there's a couple things I'm going to do here in one shot. Number 1, I'm going to take that 1/2 outside of the integral. This is supposed to be 16 minus r minus. Wait, no? That's okay. That's the square root of u. Yep.
For reduce r0 is equal to 16 instead of r is 1 over 4, I'm going to use u of 0.
This one 16 minus 4 squared, which is 16, 0. The previous one? Oh, no, that's fine. The lower bound is larger than the upper bound, right? That's fine. Because u of 0, so 16 minus 0, isn't that 16?
You plugged in 0 instead of 1.
Did I? Oh, yeah, yeah. Yeah, that's true. So that's 1, that's 1. So that's supposed to be 15, right? And let's change that to a 15. Yes, you're right. Okay, so I'm going to take out the 1/2, 0 to 2 pi, and I'm going to change the order of the limits to 0 to 15, provided I use the negative, change it to a positive. All right, so that'll be u to the 1/2 du d theta. And well, the integral of u to the 1/2, what's that? That equals 1/2 the integral from 0 to 2 pi. And I need some space in here. There we go. And that's u to the 3/2 over 3/2 from 0 to 15 d theta. Now, what is this going to be? So, okay, that's 1/2. That's 1/2 times 2/3 integral from 0 to 2 pi of 15 to the 3/2 minus 0 to the 3/2 d theta. Okay, but this 15 to the 3/2, let me do some side work. So 15 to the 3/2 is the same as saying the square root of 15 cubed. No, don't cube the number 15. That's big number. So break up the 15 cubed as 15 squared times 15. The square root of 15 squared equals to 15 root of 15. Okay? That's the number I'm going to take out of the integral. Also, these two go away, so that is 1/3 15 root of 15 integral from 0 to 2 pi d theta. And 15 over 3 reduces to 5. That's 5 root of 15. The integral of the theta, that's theta from 0 to 2 pi. And that is 5 root of 15, 2 pi minus 0, which is 10 pi root of 15. So that is the volume of this solid here. Okay. 10 pi root of 15. So there's two more problems. So let's have a look at this.
Quick question.
Yeah.
When you changed the sign of the 1/2 and you pulled it out and it flipped the upper and lower bounds at 0 and 2, should it have also flipped to 0 and 2 pi?
No, it flips one integral at a time only. Yeah, it's on one at a time. Unless we had two negative signs, then we could, but it's only one at a time.
You went from radical 16 minus x squared minus y squared. Why is that 16 minus r squared? You factor out the negative.
Yeah, I factor out the negative because, yeah.
In that radical, so that radical right there, why is that not a plus?
Because minus x squared plus y squared, factor out, and this is r squared with the negative in the front.
But you already have a leading negative. That's what I'm not understanding.
Where? Here?
You're already subtracting that quantity.
Mm-hmm.
So why is that still a minus? Can you factor out that negative 1 between the x squared and the y squared?
Yes, that's
You're already
this.
subtracting that quantity.
Mm-hmm. So yeah, that's but I mean that I'm factoring out and it remains there because this negative it's both negative. So I'm factoring one of them. That okay? Let me use a different color for this. So this square root of 16 minus x squared minus y squared. That's the same as saying 16 minus parentheses x squared plus y squared, where x squared plus y squared is r squared, right? Keep the minus 16 minus this quantity r squared. All right.
But a negative doesn't come out of there? Like that you're not pulling that negative out in front?
No, it's only for these two terms. The 16 it's still positive. Yep. It's just the remaining two terms that are negative. So I'm only factoring the negative out of these two terms. All right. Okay, let's have a look at examples 8 and 9 and wrap up the section. Maybe we'll have the chance to do one exercise, not the two of them. Okay, use a double integral to find the area enclosed by one loop of the four-leaved rows. R equals to cosine 2 theta. All right, so you might want to use your graphing calculator to graph this function, I'm going to go, okay, let me show you how we're going to graph this function. So let's make sure we have our graphing calculator is in polar mode. Number one, it's in radian mode, and it's also in function parametric. Let me go all the way to polar. Okay, second quit. Let me go about the window to make sure that I'm between 0 and 2 pi for the angle. All right. The x and the min, they're fine. Okay, let me go. So now when I go y equals, that's going to call for functions r that depend on the angle theta, or just constant functions. Well, so here I want to plot, what is that? Cosine 2 theta. Cosine 2 theta. And that's going to give us the 4-leaf rows. All right. Well, let me zoom it in. Zoom fit. I think it's 0. Yeah. So that's the graph we're looking for. Let me do it by hand on the notes. Okay. So number 1. That is, okay. All right, so, finding the area enclosed by one of the loops, and you may choose your favorite loop here. Doesn't matter. I'm going to choose the first. Well, what do I mean by the first one? The one that involves the positive x-axis. That's what I will refer as the first one. All right. Okay. So I need to find the area of that loop. But in this case, the limits of integration, what are they? I need to figure out these angles right here that are going to be the rays describing the angles. That is this ray and that other ray. I mean, the picture is not perfect, right? But it looks a lot like multiples of 45 degrees. But still, we need to show this algebraically. How are we going to find this algebraically? Well, so we're going to set this function r equals cosine 2 theta, set it equal to 0, because I need to know what are the rays that coincide with the pole. All right, that it's equal to 0. That is cosine 2 theta equals to 0. So first of all, I need to know for which angles do we have cosine equal to 0. Isn't that pi over 2? One of them is pi over 2. Another one is 3 pi over 2. And then keep going multiples at 2 pi, because these are 2 pi periodic, right? But in this case, I need to know what about theta, not 2 theta. So what I'm going to do here is multiply both sides, or multiply both sides by a half. That is, theta equals pi over 2 times a half, that's pi over 4. 3 pi over 2 times a half, that's 3 pi over 4. But the thing here is that this 3 pi over 4 is really this ray right here, all right? How are we going to go about this anyways? All right. We have a problem. I mean, this 3 pi over 2 right here, isn't that the same as 7 pi over 4 right there? Right? Pi over 4. And what's next? 3 pi over 4. All right? So let's write down the domain of integration. Number 1, so r theta, it's the set of all order pairs for which the radius, or rather, the radius r vary between 0 But in this case, notice the radii are not constant because we're not integrating over a circle. If it were a circle, then it would be 5 units all the time, 7 units all the time, depending on the radius of the circle. Here, check this out. Here, the radii, well, the radius right from the origin to this point, it's not the same as this radius or that radius or that radius, right? You see how they change based on the given function described by the for-leaf rows. So it's not going to be a constant radius. So radius goes, yes, between 0 and cosine 2 theta. And the angle varies between, okay, since in this case we want that look I shaded in green, I need to go, it will be a little weird to go between 7 pi over 4 to pi over 4, right? So how about 7 pi over 4 is the same as negative pi over 4? All right? So negative pi over 4 and pi over 4. All right? So that's the domain of integration. We're ready to set up an integral, an area integral. That is, area equals the double integral of 1 times dA. Recall that when we have a 1 in the integrand, that in double integral represents area. So that is the double integral of 1 times r dr d theta, from where the radius varies between 0 and cosine 2 theta, and the angle varies between negative pi over 4 and positive pi over 4. All right? Okay, let's do the integration with respect r. That equals the integral from negative pi over 4 to pi over 4 of that is r squared over 2, or 1/2 times r squared dr d theta. That is from 0 to cosine 2 theta. Oh, hold on. Doesn't that look like the formula you learned back in calculus 2 to find areas of polar curves? 1/2 r squared, the function squared. Again, it's just a result of evaluating a double integral, right? That's the same. Okay, so let me take out the 1/2 integral from negative pi over 4 to pi over 4. That is cosine squared 2 theta minus 0 squared d theta. Okay, yeah, that 0 squared is just 0, so we would be integrating 1/2 integral from negative pi over 4 to pi over 4. That is, what's that? Cosine squared 2 theta d theta. This is another calculus 2 type of integral because we would need one of those power reduction identities, so we may go ahead the integration. However, guys, we have a problem. Can you tell what the result of this integral would be if we evaluate it like this? 0, right? Why is that a 0? That's because look at this area at the top and the area at the bottom. Yes, my picture is not perfect, but can you see that these two areas are equal? Positive area, that is because area at the top of the positive x-axis. Negative area, that's because it's at the bottom of the positive x-axis. They're going to cancel it out. But that's not 0. I'm seeing an area. That can be 0, right? How are we going to fix this? Well, find the area of only the top part and multiply that by 2. All right? Instead, check this out. I'm going to do 2 times 1/2 the integral from 0 to pi over 4. All right? And how about we use the identity already? Okay, so to correctly use the identity, careful. The identity looks like cosine squared theta, that equals 1/2 1 plus cosine 2 theta. That is, every time every time we reduce the power of a trigonometric function, that sine and cosine, yes, we reduce the power at the cost of duplicating the angle, all right? So single angle, double angle. However, if we already have a 2 theta right here, duplicating that angle would be, isn't that cosine 4 theta? Cosine 4 theta. Yes. Careful. That's going to give us, okay, 2 times a half, they cancel out. Times the half from the identity, it's the half. Let me write it outside from 0 to pi over 4. Okay, that's 1 plus cosine 4 theta d theta. Okay, these are, let me distribute the two. Let me write down 2 integrals here. So that'll be 1/2 the integral d theta plus 1/2 the integral of cosine 4 theta d theta from 0 to pi over 4 for both. Okay, the integral of d theta, come on, that's just theta from 0 to pi over, oh wait, let me say the limits for later, and plus 1/2 times 1/4 times the integral of cosine, which is sine 4 theta from 0 to pi over 4. Okay, let me simplify this, and then upper limit minus lower limit. That is equal to 1/2 theta plus 1/8 sine 4 theta from 0 to pi over 4. All right, so that is 1/2 times upper limit, which is pi over 4 plus 1/8 sine 4 pi over 4 minus the lower limit of 0. You guys agree it's going to be both zeros when we evaluate here, and sine of 4 times 0, which is also 0. So big 0. So the only term that survives right here, sine of pi right here, that's also 0, right? So final answer, pi over 8. All right? Okay, guys. Now let's see the what ifs for this kind of problem before we leave. What if the problem said find the area of the entire flower here? Well, you don't want to integrate from 0 to 2 pi, okay? Because again, do you see positive area, negative area, positive area, negative area everywhere? Or rather, all this negative area below, all the positive area above, it's gonna give you 0 still. All right. Take the same strategy here. Find the area of one loop. Yes, you're going to run into the same situation of the positive area, negative area. So here, once you get this result, then multiply by 4 for the 4 loops. All right?